Now that I've done the brief intro to limacons and cardioids, we're going to go through these a little step by step. First of all, the term comes from the French word limaçon, which refers to small snails. So if we look at an example of maybe a limaçon with a loop, oh, let me make this a little bigger. A limaçon with a loop like this. Maybe you could use your imagination and think this is the head of the snail, his little antenna, his little face here. Here's his shell. The big part of the graph is his shell. And then, of course, here's the little slimy body that comes out underneath the shell. So I don't know if that's why it's called a small snail, but possibly. Okay, so let's think about, first of all, our sine graph. Sine graph has our 5 key points, that sine of 0 is 0, sine of pi over 2 is 1, sine of pi is 0, sine of 3 pi over 2 is negative 1, and then we would be back starting over again at pi over 2 back to 0. So if we have this equation that says 2 plus 4 sine of theta, when we put 0 in for our angle, we have 2 plus 4 times 0, or 2. That would, of course, occur every place else. So we're saying at 0 and at pi, we're going out to 2. In other words, r equals the first number, a, right there. Now, at pi over 2, sine is 1. That's when it's at its maximum. So we put pi over 2 in for theta, and we get 2 plus 4 times 1. 2 plus 4 times 1. So we're going to write this as 2 plus 4 times 0 here. So this is 6. So we go up to 6. 1, 2, 3, 4, 5, 6. That would be our high point of our graph, our maximum point. Now I just realized I plotted that one slightly wrong. That should be there. Okay. And then for when we put 3 pi over 2 in for sine of theta is negative 1 at 3 pi over 2, so we would have 2 plus 4 times negative 1, or negative 2. Now notice 3 pi over 2 in the positive, this is the positive direction for 3 pi over 2, and then the negative direction for 3 pi over 2 would be up this way. So we would actually be right here for 3 pi over 2, negative 2. Now, don't do this, but many students will take a look at these 4 points and go, oh, the graph looks like that. Or maybe they'll be a little bit more astute and they'll go, oh, there's a loop here, so it's kind of like this. But that's still way too skinny. So it's helpful if we can actually come up with another point. So I want to talk about if we had, for example, a 30, 60, 90 triangle, we could find another really nice point for sine, because opposite over adjacent at 30 degrees is 1/2. Sine of 30 is equal to 1/2. So that means at the angle pi over 6, the sine value is 1/2. So if I put in pi over 6 here, the sine of pi over 6 would be 1/2. And then I would be doing 2 plus 4 times 1/2, which is really easy. That's 2 plus 3. I'm sorry, 2 plus 2, which is 4. So at pi over 6, my radius would be 4. Now, because of symmetry, and also because I know that sine of 5 pi over 6 is the same as sine of pi over 6, because sine's positive, opposite over hypotenuse is positive in both those quadrants, then I would have another value over here that's easy to graph. Now, this gives me a better idea now of the shape of my limacon. It comes around like this, and it makes a loop, and there we go. That's what it looks like. Now I would like to equate this to the y equals 2 plus 4 sine of theta. So if I were to do y equals 2 plus 4 sine of theta, you're going to have to recall something from way back, and that is that 2 is the sinusoidal axis. That tells me how much the whole graph shifts up and down. So if I were to take the whole graph, shifting up and down. The 4 tells me how much it stretches. It's the amplitude. So that means my sinusoidal axis is now at 2. The whole graph is shifted up 2. And I go up 4, up to 6. I think I just made 3 tick marks there. Up 4, up to 6, and down 4, down to negative 2. Now if those numbers look familiar, that's because, and this is a positive 2. I know that looks like negative 2 there. That's these same numbers that we're seeing in the t-chart right here. So at 0 degrees, I'm at 2. At pi over 2, I'm up at 6. Okay, so this is pi over 2. At pi, I'm down to 2. At 3 pi over 2, I would be down at negative 2, and then back here. So my graph would look something like this. So if I were to look at my radiuses, my radii, I guess, at 0, I would have a radius of 2. That would correspond to this radius right here. At pi over 2, I'd have a radius of 6. That would correspond to this radius right here in polar form. At pi, I'd have a radius of 2. That would be the radius to the left. And then at 3 pi over 2, I would have a negative 2 radius, which would correspond to the radius of the loop. So that's how, and I'm going to probably erase those off of here now that I've drawn them, but that is how those 4 values correspond. The up and down value from the or the x-axis corresponds to the in and out radius from the center of the polar graph. So here we're measuring up or down from x. Here we're measuring out from the pole. That's the difference here. And I'm going to go ahead and take these arrows off so that the graph looks a little better. Then again, now I'm going to go put them back on here. Okay, so there's my 2, my 6, my 2, and my negative 2, which is the same radiuses that we have over on the other graph. Okay, let's do this one now. We have the same sign values, 0, 1, 0, negative 1, 0. Are now, when we add the two numbers, 4 plus 3 would be 7, because that's when sine is 0, so we just have 4 plus 3 times 0, which is 4. So we have 4s every place here. So sideways on a sine graph is going to be 4. Our highest value is 4 plus 3 times 1, which is 7. That's in the pi over 2 direction. 1, 2, 3, 4, 5, 6, 7. And then when we're at negative 1, then we'd have 4 minus 3, which is 1. So we're going to be going down 1 in the positive 3 pi over 2 direction. I'm going to do my extra value at pi over 6. Sine of pi over 6 is 1/2, so that would be 4 plus 3 times 1/2, or 5.5. So I can go out 5.5 at pi over 6 and at 5 pi over 6. Notice that value, that extra value I find, is always going to be in between the medium value and the large value. Okay? Or if I picked, say, 11 pi over 6 or 7 pi over 6, I would get a value that's in between the medium value and the smallest value, and I would have some point over here and here. I usually don't bother to find those because I think these are the most helpful. Now, if this were 4 minus 3 sine theta, and my whole graph was down here instead of up here, just like with a circle, if I make that negative amplitude negative, it's going to flip the graph over 180 degrees, then I might want to look at 7 pi over 6 and 11 pi over 6 and use a negative 1/2 in the equation instead. That might be more helpful. Now if we look at the y version of this, y equals 4 plus 3 sine of theta, we have an amplitude of 3 and a sinusoidal axis of 4. So 1, 2, 3, 4 is my sinusoidal axis. I go up 3 to 7. This is 4, and I go down 3 to 1, and so notice all of my graph is in between 1 and 7 in the y direction, just like it is in the x direction, in the radius, in the polar graph, just like the radius goes from 1 to 7, here my y values go from 1 to 7. So notice there's no loop here because there's no place where it dips below the x-axis. That's where the loop occurs, where it dips below the x-axis here. So this is actually called a limacon with a loop. And this is called a limacon with no loop, okay, or without a loop. Now the third one we have has a and b equal to each other. So I want you to notice the loop occurs when a is less than b, no loop when a is greater than b, and when they're equal to each other, that's when we get the third kind of graph, which is called a cardioid, just because it's sort of heart-shaped. So we're going to have 0, 1, 0, negative 1, and 0 for our key values for sine again. So sine of 0 is 0, so we'd have 3 plus 3 times 0. So that means where sine is equal to 0, r is just equal to the first number that's added, 3. 2, 3. Now when we have sine of pi over 2, we get 1, so we'd have 3 plus 3 times 1, which is 6. So our high value is 1, 2, 3, 4, 5, 6 right here. And then our low value would be 3 minus 3, or 0. So at 3 pi over 2, we're at 0. Adding our extra value at pi over 6, which is where sine equals 1/2, we would have 3 plus 3 times 1/2, which would be 4.5. So 4.5 here and 4.5 here. So we have a little graph that is somewhat heart-shaped, although curved, rounded at the top, not pointy like a Valentine heart. But it sort of has a heart-shaped look to it. So it's known as a cardioid. It is still a type of a limacon, but it's just the one that touches. And you'll see this in the y equals graph. And by the way, you do not have to make the y equals graph every time you graph a limacon. I just want to show you the connection between them. So here we have a case where sinusoidal axis is 3 and amplitude is 3. So this value is 3, and this is 6, and this is 0, and my entire graph is above, well, except for one point, is above the x-axis, but one point just touches the x-axis, and that's the same value that just touches the pole right here. I'm going to do one more video that's probably a little shorter than this one, just on what happens when we have cosine graphs and what happens when something is negative. So that'll be on the next page of your notes.